Hello there, and welcome to the Night Science Facts channel. Tonight, we'll be taking a slow and gentle journey through one of the most remarkable structures in the natural world, the human skeleton. Over the next couple of hours, we'll explore 100 quiet, fascinating facts about the bones that carry us through our lives. The silent architecture hidden just beneath our skin, the framework that has supported every breath you have ever taken and every step you have ever made. There is something deeply calming about bones. They are ancient, patient, and steady. While the rest of the body pulses and moves, reacts, and responds, the skeleton simply holds. It is the still center of everything you are. So before we begin, let yourself settle in. If you are lying down, let your body sink a little deeper into whatever surface is beneath you. Feel the weight of your arms, the heaviness of your legs. Let your shoulders drop away from your ears. Take one slow, easy breath in through your nose and release it gently through your mouth. There is nowhere you need to be tonight. Nothing you need to do. Just rest here and let these quiet facts about the human skeleton drift softly through your mind as you ease towards sleep. When a baby enters the world, it carries somewhere between 270 and 300 separate bones inside its small body. This number is notably higher than the 206 bones that most adult humans are said to possess. The reason for this is beautifully practical. In order to pass safely through the narrow canal of birth and to allow for the rapid growth of infancy and childhood, the skeleton begins in many more separate pieces. Over years and decades, many of these bones slowly fuse together, joining quietly at their edges, merging into single, larger structures. This process of fusion is called ossification, and it continues gradually throughout childhood and well into early adulthood. The last bones to fully fuse are often those of the spine and the collarbone, which may not be complete until a person reaches their mid-20s. It is a slow and gentle consolidation, the skeleton simplifying itself, settling into its final, mature form over the course of decades. There is something quietly moving about this. The skeleton you have now is not the one you were born with. It has changed, grown, and transformed throughout your entire life, becoming more solid and unified with each passing year. It is easy to think of bone as something static and inert, hard, white, and still. But bone is in fact a living tissue, alive and active at every moment. It contains blood vessels, nerve fibers, and several different types of cells that are constantly at work. Some of these cells, called osteoblasts, spend their time building new bone. Others, called osteoclasts, carefully break down old bone tissue. And a third type, called osteocytes, sit embedded within the bone matrix, monitoring the health and stress of the tissue around them. This ongoing activity means that your entire skeleton is quietly replacing itself all the time. Small sections of bone are dissolved and rebuilt in a continuous cycle. Over a period of roughly 10 years, almost every bone in your adult body has been substantially renewed through this process of remodeling. You are, in a very real sense, carrying a structure that has rebuilt itself from the inside out many times during your lifetime, quietly, patiently, and without any need for your attention at all. Running from the hip down to the knee, the femur, often called the thigh bone, is the longest bone in the human body. In an average adult, it measures somewhere between 45 and 50 centimeters in length, though in taller individuals, it can be considerably longer. It is also, pound for pound, one of the strongest materials found anywhere in nature. Some studies have suggested that healthy cortical bone can withstand compressive forces of up to 170 megapascals before fracturing, a figure comparable to reinforced concrete. Despite this extraordinary strength, the femur can and does break, particularly in high-energy impacts. But under the ordinary demands of daily life, walking, sitting, climbing stairs, the femur handles its loads with quiet ease, transmitting the weight of the body down toward the knee with elegant efficiency. The femur also plays a crucial role in blood production. Deep within its hollow shaft, a cavity of yellow and red marrow produces blood cells throughout a person's life. The thigh bone is not merely structural. It is also, in its quiet way, a factory. Nestled deep inside the middle ear, tucked within a tiny chamber in the temporal bone of the skull, are the three smallest bones in the entire human body. They are called the malleus, the incus, and the stapes, known colloquially as the hammer, the anvil, and the stirrup because of their shapes. Together, these three bones form a delicate chain that transmits vibrations from the eardrum to the inner ear, translating the movement of air into signals the brain interprets as sound. The stapes, the smallest of the three, is roughly 3 millimeters long and weighs about 3 milligrams, the tiniest bone in the human body, performing a task of extraordinary importance. Remarkably, these tiny bones have been with you since before birth. The ossicles reach their adult size while a person is still a fetus, meaning the ears you were born with already contained bones of nearly the same dimensions they carry today. The same small bridges of bone that helped you hear your mother's voice before you were born are still carrying every sound to your brain. The skull appears to be a single, seamless dome cradling the brain. In reality, it is a complex assembly of 22 separate bones, joined by irregular seams called sutures, which can sometimes be felt across the scalp. 8 bones form the cranium, the rounded case that protects the brain, while 14 create the facial skeleton, shaping the cheeks, nose, jaw, and eye sockets. Each bone has its own form, from the broad parietal bones of the upper skull to the thin nasal bones at the center of the face. In infants, these sutures are not yet closed, leaving soft gaps called fontanelles. They allow the skull to flex during birth and give the growing brain space to expand. By adulthood, the sutures fuse, turning the skull into a strong protective shield. When we think of what bone is made from, many people imagine calcium, and calcium is indeed a crucial component. But the primary mineral that gives bone its strength and hardness is a compound called hydroxyapatite, a crystalline form of calcium phosphate. These microscopic crystals are woven throughout the protein matrix of bone, giving it a combination of hardness and slight flexibility that makes it both strong and resistant to fracture. About 60 to 70% of the dry weight of bone is mineral, mostly this hydroxyapatite. The remaining 30 to 40% is organic material, primarily a protein called collagen. It is the interplay between these two components, the hard mineral crystals and the flexible collagen fibers, that gives bone its unique mechanical properties. Mineral alone would be brittle, like chalk. Collagen alone would be too flexible, like rubber. Together, they create something that can absorb and transmit force without breaking easily. Engineers and material scientists study bone closely because the way it combines strength with lightness and flexibility is still difficult to replicate artificially. The skeleton has been refining this formula for hundreds of millions of years. The human spine, the long column running from the base of the skull to the tailbone, is not a rigid rod, but a flexible chain of 33 vertebrae separated by soft intervertebral discs. These discs cushion movement and absorb shock. The vertebrae are arranged in 5 regions: 7 cervical in the neck, 12 thoracic in the mid-back attached to ribs, and 5 large lumbar vertebrae in the lower back. Below them, 5 sacral vertebrae fuse to form the sacrum, and 4 coccygeal vertebrae fuse into the coccyx. Viewed from the side, the spine forms a gentle S shape that distributes weight efficiently. These curves develop gradually as a child learns to hold up the head, sit, and eventually walk. This is a gentle truth. You are slightly taller in the morning than at night. The difference, usually between 1 and 2 centimeters, comes from the intervertebral discs in the spine. Throughout the day, gravity compresses the spine. The fluid-filled discs between vertebrae slowly lose a little fluid as the body carries its weight while standing and moving. By evening, the discs are slightly thinner and the spine is subtly compressed. During sleep, lying horizontally releases that pressure. The discs gradually absorb fluid again and expand. By morning, the spine has decompressed, making you a little taller. In space, where gravity is absent, astronauts can grow up to 5 centimeters taller before returning to normal height on Earth. Hidden within the hollow cavities of certain bones, red bone marrow is silently performing one of the most important tasks in the human body. Every second, it produces millions of red blood cells that carry oxygen from the lungs to tissues throughout the body. Bone marrow also produces white blood cells for the immune system and platelets that help blood clot. All of these cells originate from hematopoietic stem cells that live in the marrow and divide throughout life. In infants, red marrow fills most bone cavities, but with age, much of it is replaced by yellow marrow composed mainly of fat. Active blood-producing marrow remains concentrated in bones such as the sternum, ribs, vertebrae, and pelvis. The bones do not merely hold you up. They are, quietly and continuously, producing the very substance that carries life through your veins. The patella, the kneecap, is an example of a special category of bone called a sesamoid bone. Sesamoid bones develop within tendons rather than connecting to other bones in the usual way, forming where tendons pass over surfaces that experience strong pressure. The patella lies within the tendon of the quadriceps muscle at the front of the thigh. As the knee bends and straightens, it glides over the femur and helps increase the force of the quadriceps when extending the leg, while also protecting the knee joint. At birth, the patella is not yet bone but a mass of cartilage. It gradually ossifies during childhood and becomes fully formed by the early teenage years. There are other sesamoid bones scattered throughout the body, small ones in the foot, the thumb, and the hand. But the patella is by far the largest and most significant. The rib cage is one of the most elegantly designed protective structures in the body. 12 pairs of ribs curve outward from the spine, forming a cage around the heart, lungs, and other vital organs. It must be strong enough to protect these organs while remaining flexible enough to move with every breath. The ribs achieve this through their shape and connections. The upper 7 pairs, called true ribs, connect directly to the sternum through cartilage. The next 3 pairs, the false ribs, connect indirectly through the cartilage of the rib above. The final two pairs, the floating ribs, attach only to the vertebrae at the back. These flexible connections allow the rib cage to absorb impacts while still expanding and contracting during breathing. With every breath you take, even the quiet breath you are taking now, your rib cage is moving, expanding gently, lifting slightly, then settling back. It has done this every moment of every day since before you were born. The sternum, the flat, narrow bone at the center of the chest, develops from multiple separate cartilaginous elements that gradually fuse together during fetal development and childhood. In adulthood, it has three parts: the manubrium at the top, the body in the middle, and the xiphoid process at the bottom. The xiphoid process is the smallest part and often begins as cartilage before gradually hardening into bone with age. It can sometimes be felt just below the lower end of the sternum as a small projection. The manubrium connects with the clavicles, forming the sternoclavicular joints, the only direct bony link between the arms and the rest of the skeleton, and also supports the first pair of ribs. In medicine, the sternum has an additional significance. Because it contains red bone marrow throughout life, it is one of the sites used for bone marrow aspiration, a procedure in which a small sample of marrow is extracted for analysis. A needle is carefully introduced into the flat surface of the sternum, guided precisely to the marrow cavity within. It is a testament to how much life is quietly contained within even the flattest and most unassuming bones. The clavicle, the collarbone, is a slender S-shaped bone that runs horizontally between the sternum and the shoulder. It serves as a strut that holds the shoulder away from the body and transmits forces between the arm and the trunk. Its horizontal position and slender shape make it vulnerable to injury. A fall onto an outstretched hand or a direct blow to the shoulder can fracture the clavicle, making it one of the most commonly broken bones in the body, especially in children. Clavicle fractures have been present throughout human history. Healed fractures have been identified in Neanderthal remains more than 40,000 years old, suggesting injured individuals survived with the support of others. The clavicle is also notable for being one of the last bones to complete ossification. The medial end, the end attached to the sternum, may not be fully fused until age 25, or even later, making it one of the final bones in the skeleton to fully mature. The hand is, from a skeletal perspective, extraordinarily complex. Each hand contains 27 separate bones, 8 carpal bones in the wrist, 5 metacarpals forming the palm, and 14 phalanges in the fingers and thumb. This large number of bones gives the hand its remarkable range of motion. The fingers can bend, extend, and spread apart, while the thumb can rotate in opposition to the others, a movement essential to human tool use. The wrist can also flex and rotate because the small carpal bones glide against one another, rather than acting as a single rigid block. The carpals form 2 rows that transmit forces between the hand and the forearm. One of them, the scaphoid, is especially prone to fracture after falls and can sometimes be difficult to detect on early X-rays. Together, the 27 bones of each hand allow us to write, draw, play music, button a shirt, and hold the hand of someone we love. The hand is perhaps the most expressive part of the entire skeleton. Much like the hand, the foot contains many bones, 26 in total, plus 2 small sesamoid bones beneath the first metatarsal. These include 7 tarsals, 5 metatarsals, and 14 phalanges. The foot is designed for weight-bearing and balance rather than dexterity. The tarsals, especially the calcaneus, the large heel bone, absorb impacts from walking and running. The bones form arches, medial and lateral longitudinal arches, and a transverse arch, which act like springs, storing and releasing energy with each step and reducing forces on the skeleton. The calcaneus is the largest bone in the foot. It is the first bone to make contact with the ground at the beginning of each step, and it bears a disproportionate share of the body's weight during standing and walking. Despite this, in most people, it performs this function silently and without complaint for an entire lifetime. One of the most quietly impressive abilities of bone is its capacity for self-repair. When a bone breaks, a biological process begins almost immediately. A blood clot forms at the fracture site, creating a temporary scaffold. Over the following days, fibroblasts and chondroblasts migrate in and produce cartilage, a flexible template for new bone. After weeks, osteoblasts deposit bone mineral into the cartilage, forming a temporary callus that stabilizes the fracture. Over months, osteoclasts remodel the callus, removing excess bone and gradually restoring the bone's original shape and density. In healthy individuals, a healed fracture may eventually be almost invisible on X-ray. This capacity for healing has been essential throughout human history. Before modern medicine, broken bones were treated with splints, bandages, and immobilization, allowing the bone's own healing mechanisms to work undisturbed. The bones did the rest. The pelvis is one of the most sexually dimorphic regions of the skeleton, meaning it shows significant differences between typical male and female forms. These differences relate largely to childbirth and can help anthropologists determine biological sex from skeletal remains. The female pelvis is generally wider and shallower, with a larger pelvic inlet and a more open pubic arch. The male pelvis tends to be narrower and deeper, with a smaller inlet and thicker, more textured bones, reflecting greater muscle forces. These are general trends with individual variation, but the pelvis remains one of the most reliable bones for estimating sex in archaeological and forensic contexts, offering a quiet record of an individual's biology long after all other traces have faded. Deep in the throat, suspended between muscles and ligaments, is a small U-shaped bone called the hyoid. It sits at the base of the tongue, roughly at the level of the third cervical vertebra, and it supports the tongue and facilitates swallowing and speech. What makes it unique is that it is the only bone in the human body that does not articulate with any other bone. It floats, held in place entirely by soft tissue. The hyoid is connected to the styloid processes of the skull above by the stylohyoid ligaments, and to the thyroid cartilage below. Muscles from the tongue, the jaw, the throat, and the neck all attach to it. It acts as an anchor point for the complex muscular machinery of speaking, chewing, and swallowing. Because the hyoid is surrounded by important structures, the carotid arteries, the vagus nerve, the jugular veins, and because it can be fractured by certain types of trauma, it has forensic significance. A broken hyoid bone found in skeletal remains may indicate strangulation, though it can also be fractured in falls or other accidents, particularly in older individuals whose hyoids have fully ossified. Throughout the skeleton, at the ends of bones, in the nose, in the ears, and in many joints, there exists a tissue called cartilage. It is softer and more flexible than bone, with a smooth surface that reduces friction. But cartilage has a major limitation. It contains no blood vessels. Nutrients reach cartilage cells only by diffusion, so when cartilage is damaged, it heals slowly and incompletely. The articular cartilage covering joint surfaces does not regenerate effectively, which is why osteoarthritis, the gradual wear of cartilage, is so common and difficult to reverse. This limitation contrasts with bone, which has a rich blood supply and heals efficiently. The skeleton is not uniform. Different tissues have different strengths and vulnerabilities, each shaped by evolution for specific purposes. Despite its solidity and strength, the skeleton is surprisingly light. In a typical adult, bones make up only about 14 to 15% of total body weight. For someone weighing 70 kilograms, the skeleton weighs roughly 10 to 11 kilograms. This lightness comes from clever architecture. Long bones, like the femur and humerus, are hollow, filled with marrow, and surrounded by dense cortical bone. The ends and vertebrae contain spongy trabecular bone, a lattice that distributes stress efficiently while using minimal material. The femur can support forces many times body weight, yet weighs only about 1/3 of a kilogram, with its hollow, curved shaft maximizing strength. Nature arrived at these solutions over millions of years of evolution. Human engineers have studied and tried to replicate them in lightweight aircraft, vehicles, and building designs. Beyond their structural roles, the bones serve as the body's primary mineral reservoir, storing about 99% of calcium and 85% of phosphorus. These minerals can be released into the bloodstream as needed, helping maintain precise control of blood concentrations. Calcium is essential, not only for bone strength, but also for muscle contraction, including the heart and nerve signaling. If blood calcium drops too low, muscles can spasm, and severe deficits can be dangerous. The body draws calcium from bone if dietary intake is insufficient. Two hormones regulate this balance. Parathyroid hormone raises blood calcium by releasing it from bone, while calcitonin lowers it by promoting bone mineralization. Together, they keep calcium levels tightly controlled. The skeleton, then, is not merely a scaffold. It is also a dynamic reservoir, quietly maintaining the chemical balance that allows every organ in the body to function. Earlier, we learned that the 3 tiny bones of the middle ear, the malleus, incus, and stapes, are the smallest bones in the body. Just beyond them, in the inner ear, is the hardest bone in the human body, the petrous part of the temporal bone, which houses the cochlea and semicircular canals. Petrous comes from Latin for rock, a fitting name. This bone is extraordinarily dense, isolating the delicate inner ear structures from vibrations that could affect hearing and balance. Its hardness also makes it highly resistant to decay. In archaeological and fossil contexts, it is often the last part of a skull to survive. DNA extracted from the petrous bone is usually better preserved than from other bones, providing a valuable source of ancient genetic material. Some of the most significant ancient DNA discoveries in recent years have been made possible by the quiet durability of this one small, dense portion of the temporal bone. From birth to old age, bone undergoes a continuous process of change. In youth, bone formation outpaces bone resorption, and the skeleton grows in both size and density. Bone mass typically peaks somewhere in the late 20s to early 30s, a moment scientists sometimes call peak bone mass. From this point, the balance begins to shift, and bone resorption gradually comes to outpace formation. In the decades that follow, bone density slowly decreases. This process accelerates in women after menopause, when the loss of estrogen removes its protective effect on bone. The condition known as osteoporosis, in which bone mineral density falls below a critical threshold, makes bones more fragile and susceptible to fracture, particularly in the spine, hip, and wrist. But the changes that occur with aging are not merely a loss. Older bone also changes in its structure. The proportions of mineral and collagen shift, and the trabecular lattice within spongy bone becomes thinner and more widely spaced. The bone becomes not only less dense, but also slightly more brittle, less able to absorb energy before fracturing. Throughout this long arc of change, growing, maturing, gradually declining, the skeleton continues its quiet work, adapting as best it can to the demands placed upon it, always maintaining the body as best it is able. While 206 is cited as the standard number of bones in the adult human skeleton, this figure is an average, and the actual number varies. Some people are born with extra bones, sesamoid bones, or accessory ossicles, in the feet, wrists, or knees. Others may have bones that fail to fully fuse, remaining as separate elements. A common variation is sutural bones, or Wormian bones, in the skull. These small bones form within sutures due to differences in ossification timing. They are generally harmless, but can help identify individuals in forensic cases. Some people have an extra rib, a cervical rib, from the 7th cervical vertebra. Present in about 1% of people, they are usually asymptomatic, but can sometimes compress nerves or blood vessels. These natural variations remind us that the human skeleton, while following a consistent general plan, expresses itself differently in every individual, a unique structural portrait carried quietly throughout a lifetime. For most of human history, bones were thought to be passive structures, simply the rigid framework on which the body's active systems hung. But research has revealed that bones are far more communicative. They produce signaling molecules affecting tissues throughout the body, including the brain. One well-studied example is osteocalcin, produced by osteoblasts. Once thought to be merely structural, it functions as a hormone in the bloodstream. Osteocalcin influences memory and cognitive function, and animal studies suggest it can improve learning. It also helps regulate the body's response to acute stress, preparing the body for action. The quiet bones are, it turns out, far more active participants in the body's life than anyone imagined. They listen to the body's state and respond in kind, broadcasting their own quiet messages through the bloodstream. The shoulder, or glenohumeral joint, allows movement in more directions than any other joint in the human body. It can flex, extend, abduct, adduct, rotate, and move in a full circular arc. This range of motion comes from a large ball, the humeral head, sitting in a very shallow socket, the glenoid fossa of the scapula. The price of this mobility is stability. The shoulder relies on ligaments, tendons, and the rotator cuff muscles to keep the joint together, making it the most commonly dislocated major joint. The 4 rotator cuff muscles, supraspinatus, infraspinatus, teres minor, and subscapularis, wrap around the joint, holding the humeral head in place during the movement. They make constant adjustments to maintain stability. The mobility of the shoulder was almost certainly favored by evolution in our arboreal ancestors, for whom reaching, swinging, and hand positioning were essential. We carry that history in our flexible, slightly precarious shoulder joints. In contrast to the shoulder, the hip joint, between the femoral head and the acetabulum of the pelvis is extraordinarily stable. Where the shoulder socket is shallow, the hip socket is deep, wrapping around more than half of the femoral head. The acetabular labrum further deepens the socket, creating a suction cup effect that holds the femur firmly. Dislocating a hip requires enormous force, typically from high-energy trauma. In daily life, the hip withstands forces several times body weight without issue. The femoral head is nearly spherical, allowing rotation in all directions: flexion, extension, rotation, and outward or inward swing, supporting walking, running, climbing, and sitting. Despite its stability, the hip is vulnerable to fractures in older adults with low bone density. Yet, in a young, healthy skeleton, the hip joint remains one of the most quietly durable structures in the body. At the very top of the spine, just beneath the skull, sit two specially shaped vertebrae that allow the head its remarkable range of movement. The first cervical vertebra, the atlas, is a ring-shaped bone with no vertebral body. It sits atop the second cervical vertebra, the axis, which has an upward projection called the dens that fits into the atlas. The joint between skull and atlas allows nodding, the yes movement, while the atlas axis joint allows rotation, the no movement. Together, they give the head pivoting, nodding mobility independent of the rest of the spine. The dens is held against the atlas by a strong transverse ligament. If disrupted, it can compress the spinal cord, with serious consequences. These two ancient, specialized vertebrae have been present in our lineage for tens of millions of years, allowing our ancestors to scan their environments with fluid, responsive head movements. The large triangular bone at the base of the spine, the sacrum, takes its name from a Latin phrase meaning sacred bone. Historians suggest it may have been considered sacred because it was thought to be the seat of the soul, the last bone to decay, or associated with sacrificial offerings in ancient Rome or Greece. In ancient Egyptian medical papyri, the sacrum is mentioned in connection with lower back conditions. Galen described it in Greek medicine, noting its fusion from multiple elements. In modern anatomy, the sacrum is formed by 5 fused sacral vertebrae, completing by the mid-20s. It forms the posterior wall of the pelvis and transmits the weight of the upper body through the sacroiliac joints. It is broad, curved, deeply embedded, quiet, dense, and foundational. Whatever its sacred associations, the sacrum is certainly fundamental. It is the keystone of the pelvis, the anchor of the spine, and one of the most important weight-bearing structures in the entire skeleton. One of the most important developments in the history of medicine was the discovery of X-rays by Wilhelm Röntgen in 1895. Within weeks, their potential for visualizing the skeleton was clear. Bone, dense and mineral-rich, absorbs X-rays efficiently, appearing white, while surrounding muscles and organs appear darker. The first clinical X-ray is said to have been of Röntgen's wife, Anna Bertha Ludwig, in December 1895. Her hand bones and ring were clearly outlined against soft tissue. She reportedly said, "I have seen my death." X-rays revolutionized the diagnosis of fractures, joint disease, and bone tumors, allowing physicians to examine the skeleton non-invasively. Today, CT scans, MRI, and bone scintigraphy complement X-rays, yet the simple X-ray remains a widely used window into the body's quiet architecture. The bones of children contain more organic material, especially collagen, than adult bones, making them more flexible. When subjected to bending forces, a child's bone may deform rather than break completely. A common pattern is the greenstick fracture, where the bone bends and cracks on one side, while the other side remains intact. Another is the buckle, or torus fracture, in which the bone compresses and buckles without a full break. These patterns are almost exclusive to children. This flexibility is not a weakness. It is a quiet protection, letting young bones absorb impacts that might fracture more brittle adult bones. The 8 carpal bones of the wrist are arranged in 2 arching rows, forming the bony framework of the wrist joint. The proximal row, closer to the forearm, contains the scaphoid, lunate, triquetrum, and pisiform. The distal row, closer to the hand, contains the trapezium, trapezoid, capitate, and hamate. These bones glide slightly against one another, allowing the wrist to flex, extend, deviate toward the thumb side, radial deviation, and toward the little finger side, ulnar deviation, and to move in a circumductive arc. This range of movement is possible because the carpal bones are small enough and loosely enough connected to shift and rotate relative to one another. The scaphoid is the most commonly fractured carpal bone, typically as a result of a fall onto an outstretched hand. What makes scaphoid fractures especially challenging is that they may not be visible on early X-rays, and the blood supply to part of the bone is precarious. If a fracture disrupts this blood supply, part of the scaphoid may undergo a vascular necrosis. The bone tissue dies due to lack of blood. For this reason, persistent wrist pain after a fall is taken seriously, even when early imaging appears normal. The pisiform, the smallest carpal bone, is a sesamoid. It develops within a tendon, much like the kneecap. It is the only carpal bone classified as a sesamoid. Among the 7 tarsal bones of the foot, the talus occupies a position of exceptional mechanical importance. Sitting atop the calcaneus, the heel bone, the talus forms the lower part of the ankle joint and receives the full weight of the body, transmitted down through the tibia. It then distributes this weight to the heel behind and the rest of the foot in front. The talus is covered by articular cartilage across most of its surface, about 60%, allowing smooth motion in multiple joints. It has no muscles or tendons attached, moving entirely through the pull of surrounding bones and ligaments. Its limited blood supply makes fractures especially serious, as displaced breaks can disrupt circulation and lead to a vascular necrosis. The talus works quietly at the hub of the foot and ankle, managing extraordinary forces with each step. If you were to look at a section of cortical bone under a microscope, you would see that it is not a uniform, homogeneous material. It is organized into cylindrical units called osteons, also known as Haversian systems, each consisting of a central canal surrounded by concentric rings of bone matrix, like the rings of a tree trunk. Each central canal carries a blood vessel and a nerve fiber, supplying the bone cells around it. The rings are formed from layers of collagen fibers whose orientation alternates between layers, distributing stress and making bone resistant to fractures. Older, partially degraded bone fills spaces between osteons in a mosaic pattern representing previous generations of bone. The organized, grain-like structure of bone is visible even to the naked eye in some circumstances, as the subtle pattern of lines known as the lines of Zahn. Bone is not merely hard, it is intricately patterned. Within the bones of the face and skull, tucked into the dense bone surrounding them are a series of air-filled cavities called paranasal sinuses. There are 4 pairs: the maxillary sinuses in the cheekbones, the largest, the frontal sinuses behind the forehead, the ethmoid sinuses between the eyes, and the sphenoid sinuses deep in the skull. All of these sinuses connect to the nasal cavity through small openings. The sinuses reduce the weight of the skull and may help resonate the voice. Lined with mucous membrane, they produce mucus that drains into the nasal cavity, humidifying and warming inhaled air while participating in immune defense. When inflamed, fluid accumulation causes sinusitis, sometimes producing pain resembling toothache from nearby upper molars. The shape and size of the sinuses vary between individuals and are often visible on X-rays and CT scans. Like fingerprints, their specific configuration can sometimes be used for identification. Medical terminology for bones is largely derived from Latin and Greek, and some of these names carry long histories. The thigh bone's anatomical name, the femur, is simply Latin for thigh. But the longest single-word name for any bone in the standard human skeleton belongs to a small, flat bone on the inner side of the foot, the os naviculare pedis, or, more commonly, simply navicular, from the Latin for little boat, describing its curved, boat-like shape. Many bones carry names describing their shape or resemblance to other objects. The hamate is named for its hook-shaped process, from the Latin for hook. The pisiform is named for its resemblance to a pea, from the Latin pisum. The trapezium and trapezoid are named for their roughly trapezoidal shapes. The clavicle comes from the Latin for little key, because its shape was thought to resemble the keys used in ancient Rome. The naming of bones reflects centuries of anatomical observation and scholarship, carried out by physicians and scientists across many cultures. Some names date back to ancient Greece. Others were assigned during the Renaissance flowering of anatomical study. The names are a quiet lexicon of observation, each one a small piece of the history of human curiosity about the body. The eye is arguably the most delicate of the major sensory organs, and the skeleton invests considerable structure in its protection. The orbit, the bony socket housing the eye, is formed by no fewer than 7 different bones, contributing to a roughly cone-shaped cavity that cradles the eyeball and the muscles, nerves, and blood vessels that serve it. The bones forming the orbit include the frontal bone above, the zygomatic at the outer lower corner, the maxilla along the lower inner floor, and smaller contributions from the lacrimal, ethmoid, sphenoid, and palatine bones. The orbital rim is thick and robust to absorb impacts, while the floor and medial wall are thin and may fracture under blunt trauma, a pattern called a blowout fracture. This design acts like a pressure release valve, protecting the eyeball. The tear duct, the lacrimal duct, runs through a groove in the lacrimal bone at the inner corner, draining tears into the nasal cavity. This is why crying or having watery eyes often produces a runny nose. Long before a baby is born, the skeleton is already taking shape. Bone development begins in the embryo during the 5th or 6th week, forming from neural crest cells and mesoderm. Most of the skeleton forms through 2 processes. In endochondral ossification, a cartilage model forms first and is gradually replaced by bone, as in long bones, vertebrae, and the skull base. In intramembranous ossification, bone forms directly within connective tissue sheets, as in the flat bones of the skull and much of the face. By birth, primary ossification centers are established, though much skeleton remains cartilage. Secondary centers appear in long bone ends during childhood and adolescence, eventually fusing with the shaft. The timing of these events forms a quiet developmental calendar written in bone. One of the most important developments in bone health has been dual-energy X-ray absorptiometry, or DEXA. This technique uses very low-dose X-rays at 2 energy levels to measure bone mineral content, most often in the spine and hip. Results are expressed as a T-score, comparing bone density to a young adult at peak mass. Scores above -1 are normal. -1 to -2.5 indicates osteopenia. Below -2.5 indicates osteoporosis. T-scores guide preventive treatment decisions for fracture risk. DEXA scans are quick, painless, and expose patients to very little radiation. Repeated scans track changes over time, monitoring treatment effects or natural aging. This ability to quantify bone density non-invasively allows early, precise identification of risk, quietly and without harm. Unlike most bones, which begin ossifying in fetal life, the patella is late to mineralize. Its cartilaginous precursor is present early, but ossification, true hardening, typically starts between ages 3 and 5. The patella often ossifies from multiple centers that gradually merge into a single bone by early adolescence. In about 2% of adults, one center remains separate, forming a bipartite patella. This fragment is usually asymptomatic and often discovered incidentally on X-rays. The kneecap's late development reflects its role as a sesamoid bone within the quadriceps tendon. Mechanical stress from movement after birth stimulates ossification, allowing the patella to grow in response to activity. Studies of archaeological skeletal remains show that humans tens of thousands of years ago, hunter-gatherers walking long distances and performing demanding physical work, had denser, more robust bones than most modern people. Pre-agricultural bones often display greater cortical thickness, larger cross-sectional areas, and higher strength indices, reflecting a lifestyle of extensive walking, carrying, and climbing. Bone responds to mechanical loading by becoming stronger, a principle known as Wolff's Law. Our bones serve as a biography of our physical lives, shaped and strengthened by every step, load, and climb we have ever undertaken. The brain, arguably the most critical organ, is encased in the skull, a protective structure of remarkable engineering. Its interior cradles the brain's contours, reducing movement and impact. 3 layers of membrane, the meninges, further cushion the brain. The dura mater is tough and fibrous, the arachnoid mater thin and web-like, and the pia mater clings to the brain's surface. Cerebrospinal fluid in the subarachnoid space acts as a liquid shock absorber. Despite this protection, skull fractures can be serious, particularly if blood vessels are torn. Skull thickness varies. Frontal and parietal bones are thickest, while the temporal squama above the ear is relatively thin, a naturally vulnerable point. The human foot takes an extraordinary pounding. With each step, its bones and joints absorb forces equal to 1 to 1.5 times body weight in walking, and more in running or jumping. Over a day, this can mean thousands of compressions and stretches of bones, cartilage, and connective tissues. Remarkably, most feet function silently for millions of steps. The foot's architecture, arches, articular surfaces, intrinsic muscles, and long tendons, distributes and manages these forces efficiently. The calcaneus contacts the ground first, absorbing impact. The foot rolls forward through the midfoot, then pushes off with the toes. Heel strike, mid-foot loading, toe off. This sequence repeats every day, quietly propelling the body forward. Of all the bones in the skull, 22 joined at sutures. Only one is freely movable. The mandible, the lower jaw, connects to the skull at the temporomandibular joints, allowing it to open and close, slide forward and backward, and shift slightly side to side, essential for chewing, speaking, and swallowing. The joint has an articular disc of fibrocartilage, dividing it into upper and lower compartments, enabling hinge-like and sliding movements. The mandible also holds the lower teeth in alveoli, which gradually resorb after tooth loss, changing jaw shape. Dense and well positioned, the mandible is among the best preserved bones archaeologically, revealing insights into human evolution, diet, and identity over millennia. At the very base of the human spine, below the sacrum, lies the coccyx, a small curved structure formed by the fusion of 3 to 5 tiny vertebrae. In most adults, it is a single bone, though sometimes 2 or more pieces remain. It represents the evolutionary remnant of a tail. Unlike the long tails of other mammals, the human coccyx is reduced and bears no weight during standing or walking. It serves mainly as an attachment site for muscles and ligaments of the pelvic floor and gluteal region. Though uncommon, coccyx fractures are extremely painful when sitting, often treated with cushions, pain relief, and time. As a vestigial structure, it reflects reduced function over evolution, retaining only minor roles while preserving a trace of its ancestral form. The upper arm contains a single bone, the humerus. The forearm contains 2, the radius on the thumb side and the ulna on the little finger side. These names come from Latin. The humerus simply means upper arm. The radius refers to a spoke or ray, highlighting its role as the bone that pivots around the ulna during rotation. The ulna means elbow, referencing its prominent olecranon process. This arrangement gives the forearm remarkable rotational ability. During pronation, the radius crosses over the ulna. During supination, it returns parallel. Rotation occurs at both the proximal and distal radio-ulnar joints. The radius bears most of the load from the hand to the elbow and directly connects with the wrist carpals. This 2-bone design is an ancient vertebrate feature, refined over hundreds of millions of years. What most people call the elbow joint is actually 3 distinct joints within a single capsule. The humerulnar joint, between the humerus and ulna, acts as a hinge for flexion and extension. The humeroradial joint, between the humerus and the radius, aids both bending and rotation. The proximal radio-ulnar joint, between the radius and ulna, allows forearm rotation independently of bending. All 3 share a synovial space, so a single injection or inflammation affects them all. The ulna's olecranon fits into a humeral fossa when extended, preventing hyperextension and stabilizing the joint. The humerus's medial epicondyle anchors wrist and finger flexors. Striking it compresses the ulnar nerve, producing the tingling known as the funny bone. At the ends of every long bone in a growing child lies the epiphyseal growth plate, or physis, where bones lengthen over childhood and adolescence. Here, chondrocytes multiply in columns, enlarge, deposit matrix, and die, forming a scaffold that blood vessels invade and replace with bone, adding incremental length with each cycle. Hormones, including growth hormone, insulin-like growth factor, thyroid hormones, and sex hormones, along with mechanical signals, regulate this process. Because the growth plate is cartilage, it is weaker than surrounding bone, making it prone to fractures that can disrupt growth. Once growth is complete, the cartilage is fully replaced. The epiphysis fuses with the shaft, and longitudinal bone growth ceases, marking skeletal adulthood. Forensic anthropologists can often infer ancestry from skeletal remains. Skull shape, dental traits, and skeletal proportions reflect long-term evolutionary histories, so populations from the same region share subtle features. Traits include nasal aperture shape, cheekbone projection, eye orbit form, palate structure, and tooth crown details. No single feature is definitive, but combinations can indicate probable ancestry. A clear example is the shovel-shaped upper central incisor, common in East Asian and indigenous American populations, rare in Africans, and linked to the EDARV370A gene, which also affects hair and sweat glands. The skeleton quietly records ancestry, showing how evolution shaped human form across generations. The health and strength of the skeleton are profoundly influenced by nutrition throughout life, especially during infancy, childhood, and adolescence. Calcium and phosphorus are the main mineral components, while vitamin D is essential for calcium absorption and proper bone mineralization. Severe vitamin D deficiency prevents proper mineral deposition. In children, this causes rickets, with soft, bowed bones. In adults, osteomalacia, or soft bone, leads to weakness and fractures. Historically, rickets was common in industrialized Northern Europe due to limited sunlight, and today, mild deficiencies still affect bone health globally. Adequate nutrition in early life builds the bone density reserve the body relies on later. The food consumed in the first 2 decades is a vital investment in a skeleton that will support the body for decades to come. When humans evolved to walk upright, the spine had to adapt to new mechanical demands. Unlike quadrupeds, whose spines act as horizontal beams, the human spine functions as a vertical column, managing the upper body's weight through its S-shaped curves. Cervical and lumbar lordosis and thoracic kyphosis. These curves improve shock absorption and energy storage with each step. Lumbar lordosis, the inward curve of the lower back, is uniquely human. Great apes have outward curving, rigid lower spines. This curve underlies our posture and develops alongside upright walking in childhood. The evolution of bipedalism, combined with a larger brain and narrower pelvis, is a central story of human evolution, a story quietly recorded in bone. When unidentified skeletal remains are found, forensic anthropologists estimate age at death using different markers for children and adults. In children, skeletal development, ossification centers, epiphyseal fusion, and tooth eruption provides reliable age estimates, often within a few years. Teeth are particularly consistent across populations and highly informative. In adults, markers are less precise. Age-related changes in the auricular surface of the ilium, the pubic symphysis, skull suture closure, joint osteoarthritis, and microscopic bone structure all offer clues. Multiple methods are combined to produce an age range. For example, 20 to 35 years for young adults, 50 to 70 for older individuals. Even an approximate range is valuable for identifying remains or studying the demographics of past populations. The foot's 3 arches, medial longitudinal, lateral longitudinal, and transverse, are dynamic, not rigid. They flatten under load and rebound when unloaded, acting like springs to improve walking and running efficiency. As the foot flattens, the plantar fascia stretches, storing elastic energy. When the heel lifts and toes extend, this energy is released, aiding forward propulsion. This spring-like action significantly contributes to human locomotion efficiency. Arch development and maintenance rely on intrinsic foot muscles and long leg muscles whose tendons insert into foot bones. Weakness or plantar fascia issues can flatten the arch, altering gait and increasing injury risk. Infants are born with flat feet, padded with fat. The arch forms over early childhood as standing, walking, and muscle strengthening shape the bones and ligaments into their mature configuration. One of the most elegant mechanical arrangements in the skeleton is the relationship between the radius and ulna in the forearm. Rather than being simply side by side like two parallel bars, these two bones are designed to rotate around each other, allowing the forearm its ability to pronate and supinate. The head of the radius, at the elbow, is a smooth cylinder that rotates within a ring formed by the annular ligament and the radial notch of the ulna. At the wrist, the dome-shaped head of the ulna fits into the ulnar notch of the radius. As the radius rotates over and around the ulna during pronation, its lower end sweeps across the front of the ulna, carrying the hand from a palm up to a palm down position. This axis of rotation runs from the center of the radial head at the elbow to the center of the ulnar head at the wrist, a diagonal line passing through the forearm. Holding a glass of water and rotating it between palm up and palm down, you can trace the movement produced by this beautifully simple joint arrangement. The ability to pronate and supinate has been enormously important in human tool use and in many everyday activities. Turning a doorknob, using a screwdriver, typing on a keyboard, all require this forearm rotation. Some other animals have lost this ability through evolution as their forelimbs became specialized for other purposes. Humans retain it in full, and it has served us well. The femoral neck, the angled section connecting the thigh bone's head to its shaft, beautifully illustrates how bone adapts to stress. Its trabecular bone is not random, but forms two systems of arching struts aligned with the main stress directions during standing and walking. In the 19th century, Carl Kuhlmann noted the similarity between these trabecular patterns and stress lines in mechanical cranes. Julius Wolff used this as evidence for Wolff's law. Bone remodels according to the forces placed upon it. Modern studies confirm that osteocytes sense mechanical strain and guide remodeling, so the femoral neck structure records every load it has borne, a quiet architectural autobiography in bone. The temporal bone, forming the sides and base of the skull, is highly complex. It houses the structures of hearing and balance, the ear canal, the middle ear with its 3 ossicles, the cochlea, semicircular canals, and vestibular apparatus. It also carries the facial nerve through the narrow facial canal to the muscles of facial expression. The mastoid process behind the ear contains air cells connected to the middle ear, lined with mucous membrane. Before antibiotics, infection spreading here, mastoiditis, was dangerous. The internal auditory canal in the petrous portion carries the vestibular cochlea and facial nerves, often imaged by MRI for hearing or balance issues. The temporal bone is commonly fractured in head injuries, which can affect hearing and facial nerves, though the dense petrous portion often protects the delicate inner ear structures within. Bones do not act alone. Ligaments, tough bands of fibrous tissue, connect bones, guiding and limiting joint movement, while tendons attach muscles to bones, transmitting muscular force to produce movement. At attachment sites, a specialized zone called the enthesis transitions, gradually from fibrous tissue into mineralized bone via fibrocartilage. This distributes stress, reducing force concentration, but also makes the enthesis prone to overuse injury. Inflammation here, enthesitis, occurs in certain arthritic conditions, such as ankylosing spondylitis. Bones respond to repeated pulling by developing surface features, ridges, tuberosities, or rough patches, visible on skeletal remains. These markings reflect habitual activity and muscular development, providing anthropologists with insights into an individual's lifestyle and physical stresses. The human spine, viewed from the front or back, should appear as a nearly straight vertical line. In some individuals, the spine develops a lateral curvature, a sideways bend, that may also involve rotation of the vertebrae. This condition is called scoliosis. Scoliosis affects a small but significant proportion of the population, typically becoming apparent during the adolescent growth spurt. Most cases are classified as idiopathic, meaning the cause is not known, though genetic factors are thought to play a role. The curvature may be mild and remain stable throughout life, requiring no treatment other than monitoring, or it may progress during growth and require bracing or, in more severe cases, surgical correction. Mild scoliosis is often detected by school screening programs in which students are examined for asymmetry of the shoulder blades, waist, or rib cage when bending forward. More detailed assessment uses standing full spine X-rays to measure the angle of curvature. Scoliosis has been documented in human skeletal remains throughout history. The famous portrait of Richard III, the 15th century King of England, has long been associated with descriptions of a crooked back. And when his skeleton was discovered beneath a Leicester car park in 2012, it was found to show a significant adolescent onset idiopathic scoliosis, a vivid historical confirmation written in his bones. We began our journey by noting that infants have more bones than adults. Over childhood and adolescence, many separate bones gradually fuse into single structures, a process occurring across the skeleton. The skull demonstrates this clearly. Vault bones start as separate plates, separated by flexible sutures and fontanelles at birth. These sutures close over the first years of life, forming rigid interlocking joints, though the lines remain visible throughout life. The sacrum forms from 5 vertebrae fusing between childhood and the mid-20s, and the coccyx from 3 to 5 vertebrae, usually completing in adulthood. The sternum ossifies from multiple centers during growth. At the skull base, several bones fuse early, including the sphenoid, forming the complex base that supports the brain and articulates with the spine. Thus, the skeleton grows and simplifies simultaneously, gaining length and mass while reducing separate elements, moving from the fragmented flexibility of infancy to the unified solidity of maturity. Here is a quietly counterintuitive anatomical truth. The wrist has no intrinsic muscles capable of moving it. All muscles that flex, extend, or deviate the wrist are located in the forearm, with tendons crossing the wrist to insert into carpal bones and metacarpal bases. The wrist itself is passive, moved entirely by these tendons. This arrangement is highly efficient. Forearm muscles, with large cross-sectional areas, generate substantial force, transmitted through slender tendons across the wrist to the hand. The carpal bones act as pulleys and levers, redirecting and distributing these forces. The fingers follow the same principle. Long flexor and extensor tendons from the forearm pass along the fingers, allowing motion at a distance. The hand's intrinsic muscles, small and located within the hand, primarily control finger and thumb movements, enabling fine dexterity rather than wrist motion. One of the most compelling demonstrations of evolutionary relationship is the shared structure of vertebrate limbs. The human forelimb, batwing, whale flipper, horse leg, and gorilla arm all follow the same fundamental arrangement. A single upper bone, humerus, two lower bones, radius and ulna, a cluster of wrist bones, carpals, then metacarpals, and finally digits, phalanges. This pentadactyl pattern arose in early tetrapods some 375 million years ago and has been adapted for diverse lifestyles. In bats, hand bones elongate to support wings. In whales, fingers are embedded in flippers. In horses, most digits are lost, leaving a single toe. Humans retain this ancestral plan in a relatively conservative form: 5 digits, separate radius and ulna, and an articulated wrist. Every hand reflects a design shared with bats, whales, and horses, preserved for nearly 400 million years. Between each vertebra in the spine lies an intervertebral disc composed of a tough outer ring, the annulus fibrosus, surrounding a gel-like core, the nucleus pulposus. These discs cushion the spine, distribute loads across vertebral end plates, and allow slight movement between vertebrae. Over time or under repeated stress, the annulus can weaken and tear. The nucleus may bulge or extrude through such tears, forming a herniated disc. If this presses on spinal nerves, it causes pain, numbness, or weakness. In the lumbar spine, herniation often affects L4 to L5 or L5 to S1, producing sciatica. In the cervical spine, symptoms may radiate into the arm. The nucleus is mostly water and proteoglycans, largely avascular, and loses hydration with age, reducing its shock-absorbing ability. This contributes to gradual height loss and diminished spinal resilience over the decades. When comparing modern human skulls with those of extinct relatives, Australopithecines and early Homo species, the evolutionary changes are written in bone. The most striking change is the expansion of the cranium as brain size increased. Australopithecines had brain volumes around 400 to 550 cubic centimeters. Early Homo, such as Homo habilis, about 600 to 700 cubic centimeters, and later species, including Homo heidelbergensis and Neanderthals, reached 1,200 to 1,500 cubic centimeters, overlapping modern human ranges. As the brain grew, the skull shape shifted. The cranium became higher and rounder, brow ridges reduced, and the face flattened beneath the brain. Large cranial crests for jaw muscles disappeared as jaws became smaller. Teeth also reduced in size, reflecting dietary changes such as the use of cooked food. Each skull in this lineage preserves a quiet record of brain size, diet, and habitual forces, showing evolution etched directly in bone. Because red bone marrow produces all blood and immune cells, diseases originating there, including leukemias, lymphomas, and inherited disorders like sickle cell disease, can sometimes be treated by replacing the marrow with healthy donor cells, a procedure called a bone marrow or hematopoietic stem cell transplant. The patient's diseased marrow is first destroyed with high-dose chemotherapy or radiation. Donor stem cells are then infused, migrate to the bone cavities, and begin producing new blood cells. Matching donor and recipient is crucial, primarily via the human leukocyte antigen, HLA, system, to reduce the risk of graft versus host disease. This use of the skeleton as a platform to rebuild the blood and immune system remains one of the 20th century's most profound medical advances. Just as bone remodels under mechanical stress, habitual activities leave distinctive marks on the skeleton that trained anthropologists can interpret. These occupational or activity markers include unusual bone density patterns, enlarged or reshaped muscle attachment sites, atypical joint wear, and specific enthesial changes. Musicians, like violinists, often show asymmetric arm bone development, while Roman gladiators exhibit joint wear and enthesial changes from combat training. Medieval archers display remodeled bow arm bones, and agricultural workers who ground grain show characteristic shoulder, elbow, and knee modifications. Habitual squatting produces distinctive facets on ankle bones. Though probabilistic rather than definitive, these skeletal signatures preserve a subtle biography of how an individual moved through life, long after other traces have disappeared. The knee joint, connecting the femur, tibia, and patella, is primarily a hinge, allowing flexion and extension, but it also incorporates subtle rotation, making it more complex than a simple hinge. As the knee straightens, the tibia rotates slightly outward relative to the femur in the screw-home mechanism, locking the joint for stability and reducing muscular effort. The popliteus muscle unlocks this rotation to initiate bending. Two C-shaped fibrocartilage discs, the medial and lateral menisci, sit between femur and tibia, deepening the joint surface, distributing load and aiding stability and lubrication. Four major ligaments, anterior and posterior, cruciate inside the joint, and medial and lateral collateral on the sides, stabilize the knee while permitting controlled movement. The fossil record of human evolution spans millions of years, preserving bones and teeth through mineralization, where water deposits minerals that replace organic tissue, creating rock-like casts. Some of the oldest hominin fossils are from Ethiopia, notably Lucy, an Australopithecus afarensis who lived around 3.2 million years ago. Her skeleton, including the knee joint, confirmed upright walking long before brain expansion. Even older remains, like Sahelanthropus chadensis from 6 to 7 million years ago, consist mainly of a cranium found in Chad, fueling decades of study on early human locomotion. Each fossil fragment represents a journey through time, preserving in stone the life that once animated it. On the palm side of the wrist, the carpal tunnel is a narrow passage formed by the carpal bones and the flexor retinaculum. It carries 9 tendons, the long flexors of the fingers and thumb, and the median nerve, all tightly packed. Compression of these structures from swelling, repetitive use, or anatomical variation irritates the median nerve, producing carpal tunnel syndrome, tingling, numbness, and pain in the thumb, index, middle, and half of the ring finger, often worse at night. Common causes include prolonged wrist flexion, repetitive hand tasks, pregnancy, thyroid disorders, and rheumatoid arthritis. Treatments range from night splints to surgical release of the retinaculum, which immediately relieves pressure. The carpal tunnel illustrates how the skeleton and soft tissues share confined spaces, arrangements that are normally efficient but can become problematic. Although teeth are technically distinct from bone in their composition and developmental origin, they are generally considered part of the skeletal system, as they are mineralized structures that contribute to the rigid framework of the body and are essential to its mechanical function. Teeth are composed of several distinct tissues. The outermost layer, the one visible above the gum, is enamel, the hardest tissue in the human body, harder even than bone. Enamel is made almost entirely of hydroxyapatite crystals, with very little organic content, and unlike bone, it cannot regenerate once fully formed. Beneath the enamel lies dentine, also mineralized, but softer than enamel and more similar in composition to bone. The core of each tooth, extending into the root, is the pulp, soft tissue containing nerves and blood vessels. The roots of teeth are embedded in bony sockets in the jaw, anchored by a specialized ligament called the periodontal ligament. This ligament is not merely a passive anchoring structure. It is sensory and dynamic, conveying information about biting forces to the brain and allowing slight movement of the tooth within its socket. Teeth are extraordinarily durable. They survive long after death, often outlasting all other skeletal elements in the archaeological record. The state of the teeth, their wear patterns, the presence of decay, the mineralization of dental calculus, provides rich information about an individual's diet, health, and age, making them among the most informative elements of any skeletal assemblage. Earlier, we noted that the clavicle, the collarbone, is the last bone to complete ossification. Its medial end, where it meets the sternum, fuses between ages 22 and 30, later than most other epiphyses. This late fusion is important in forensic anthropology and radiology. An unfused medial clavicle indicates incomplete skeletal maturity and can help estimate age around legal adulthood. The clavicle is also unusual in ossifying directly in connective tissue, intramembranous ossification, starting in the 5th week of fetal life. In this way, it has the longest ossification period of any bone, beginning extremely early and finishing last. From early fetal development to the late 20s, the clavicle quietly grows, develops, and consolidates. Bones and teeth quietly record stress during growth, preserving it as permanent markers. One striking example is the Harris line, a dense transverse band on long bones formed when growth temporarily halts due to illness, malnutrition, or stress, then resumes. Teeth show similar evidence. Enamel hyperplasias, horizontal lines, furrows, or pits, mark temporary reductions in enamel formation. Their position allows estimation of the age when the stress occurred. Archaeologists use these markers to study childhood health and nutrition. Populations with poor diet or high disease burden show more Harris lines and enamel hyperplasias. Bones and teeth are not just structures. They are personal histories, recording hardships and recovery at the cellular level across centuries. Most vertebrae have a cylindrical body at the front and a bony arch at the back, enclosing the spinal canal. The atlas, the first cervical vertebra, is unique. It has no body, forming a bony ring with thickened anterior and posterior arches connected by lateral masses that articulate with the skull above and the axis below. Evolution explains this absence. The body that would belong to the atlas fuses with the axis to form the dens, around which the atlas rotates. During development, the dens initially forms with the atlas segment before fusing with the axis. This ring shape is immediately recognizable, allowing a generous canal for the spinal cord and accommodating rotation at the atlantoaxial joint. The atlas's unusual anatomy reflects the mechanical demands of supporting and moving the skull while permitting extensive head rotation. Identical twins share the same DNA. Their genome is essentially the same. yet their skeletons are not perfectly identical. Studies comparing skeletal dimensions in identical twins have consistently found that while twins are more similar to each other than to unrelated individuals, there are still measurable differences in bone length, density, and proportions. These differences arise partly from environmental influences during development, different positions in the womb, different nutritional environments, subtle differences in physical activity after birth. They also reflect the role of chance in the development of any complex biological structure. Even with identical genetic instructions, the actual process of growth involves countless individual cellular events, each of which has a small element of randomness. This finding illustrates a broader truth about the skeleton. While its general form is strongly shaped by genetics, its specific details are shaped by the interaction between genes and the environment and experience of each individual life. Bone density reflects nutrition and physical activity. Bone shape reflects the forces of muscle and gravity. Even the pattern of sutural bones in the skull is partly influenced by the mechanical environment of the developing brain. The skeleton is not simply a genetic blueprint made physical. It is the record of a life, the accumulated result of every meal eaten, every step taken, every illness overcome, from the moment of conception to the present day. One of the most successful medical interventions of the 20th century has been total joint replacement, substituting a damaged natural joint with an artificial one of metal, plastic, and ceramic. Hip and knee replacements are most common, though shoulder, elbow, ankle, and finger joints are also replaced. In a total hip replacement, the worn femoral head is removed and replaced with a metal stem and ball, while the acetabulum is lined with a metal cup and plastic liner for smooth articulation. The materials mimic the original joint, and surfaces are designed for bone to grow onto them, osseointegration, securing the implant. Hundreds of thousands of these procedures are performed yearly. For patients debilitated by arthritis, joint replacements restore mobility and quality of life, showing how the skeleton can partner with human engineering to support the body in later years. When astronauts spend long periods in weightlessness, their skeletons change dramatically. Without gravity, bones bear little load, and osteocytes detect the absence of stress, shifting the balance toward bone resorption. This leads to progressive bone density loss, especially in the lower body. Studies show astronauts can lose 1 to 2% of bone density per month, far faster than typical osteoporosis. After 6 months in space, hip and lower spine density can drop significantly, and some may not fully recover even after a year back on Earth. This illustrates how dependent bones are on mechanical load. Remove it, and the skeleton quietly dissolves, returning mineral to the bloodstream. Understanding this has improved strategies to preserve bone health on Earth and in space. The scapula, the shoulder blade, is a flat, triangular bone lying against the back of the rib cage, connected to the skeleton only at the acromioclavicular joint with the clavicle. This single connection allows the scapula to slide across the rib cage in multiple directions under muscular control. It can tilt, rotate, glide, and protract, movements essential for overall shoulder mobility. Upward rotation of the scapula contributes about 60 degrees to arm elevation, enabling the full range of motion. The scapula provides attachment for key muscles, the subscapularis on the front, the infraspinatus and teres minor on the back, and the serratus anterior along the medial border. Weakness of the serratus anterior causes a winged scapula, where the inner border sticks out from the back. By combining freedom of motion with muscular attachments, the scapula is both a stable platform and a dynamic participant, central to the versatility of the human shoulder and arm. The study of the skeleton spans thousands of years. In ancient Greece, Hippocrates described fractures and dislocations accurately and wrote about their treatment. Galen, a 2nd century physician, detailed the skeleton largely through animal dissection, using monkeys as human models. During the Islamic Golden Age, physicians like Ibn Sina, Avicenna, produced encyclopedic medical texts describing the skeleton, extending Greek knowledge. His canon of medicine remained influential in both the Islamic world and Europe for centuries. The Renaissance transformed anatomy. Andreas Vesalius, in 16th century Padua, performed systematic human dissections and published De Humani Corporis Fabrica, 1543, with precise illustrations that corrected many Galenic errors. Over 2 millennia, careful observation and recording quietly built the foundation for modern anatomy and medicine. The kneecap, despite being a small, roughly circular bone of modest appearance, has a dedicated and somewhat complex blood supply. It is supplied by a network of vessels derived from several arteries that form an anastomosis, a series of connections and loops around the knee. This network is important because the patella, unlike most other bones, does not have a periosteum, the fibrous outer layer of bone that carries blood vessels, over most of its surface. The anterior surface, the front, toward the skin, is covered by the quadriceps tendon and patella tendon, through which blood vessels enter. The posterior surface is covered by cartilage, which has no blood vessels. Blood, therefore, reaches the patella mainly through the tendinous connections at its periphery and through the retinacular vessels running along its sides. This somewhat precarious supply can be disrupted by displaced fractures of the patella or by surgery, potentially leading to a vascular necrosis, the same problem that can affect the femoral head and scaphoid. For this reason, surgeons repairing patella fractures take care to preserve the soft tissue attachments that carry the blood supply, avoiding excessive stripping of the tendon and retinacular tissue. Despite these considerations, the kneecap's blood supply is in most circumstances robust enough to sustain it through a lifetime of heavy use, a quiet efficiency that tends only to be noticed in its absence. The skull contains numerous holes called foramina, through which nerves and blood vessels pass to the face, brain, and neck. Each foramen has a specific location and function. The foramen magnum is the largest, allowing the brainstem to continue as the spinal cord. The carotid canals carry the internal carotid arteries, and the jugular foramina carry veins and cranial nerves. 9, 10, and 11. The optic canals transmit the optic nerves. Other cranial nerves exit through foramina like the stylomastoid, supraorbital, infraorbital, and mental foramina. These landmarks are critical for surgeons and radiologists. Forensic anthropologists can also study foramina, as their size and wear patterns may reveal information about the vessels and nerves that passed through them in life. Joints, or articulations, are where bones meet, and they are classified by the amount of movement they allow: fibrous, cartilaginous, or synovial. Fibrous joints connect bones with dense tissue and allow little or no movement. Examples include the sutures of the skull and the gomphoses of teeth. Cartilaginous joints allow limited movement. Synchondroses use hyaline cartilage, like rib sternum joints, or growing long bone epiphyses, while symphyses use fibrocartilage, like the pubic symphysis or intervertebral discs. Synovial joints are highly mobile, with a fluid-filled cavity lined by a synovial membrane and smooth articular cartilage. Major limb joints, hip, knee, shoulder, elbow, wrist, ankle, are synovial. Different joint types meet different functional needs: stability, slight flexibility, or free movement. The human skeleton is roughly bilaterally symmetrical, with left and right bones of the limbs, skull, pelvis, and ribcage forming pairs. These pairs develop from the same genetic instructions in similar environments, making them very similar, though not perfectly identical. Minor differences arise from random developmental variation or habitual use. Handedness, for example, causes the dominant arm to show slightly greater bone mass, altered muscle attachment sites, and subtle differences in shape compared with the non-dominant arm. Even the skull shows slight asymmetries, reflecting the unequal structure and function of the brain's hemispheres. These small variations are measurable, but usually go unnoticed in daily life. The ankle joint, the articulation between the tibia, fibula, and talus, is sometimes described as a mortise and tenon joint, borrowing a term from carpentry. In woodworking, a mortise is a slot cut into one piece, and a tenon is a projecting tongue on another piece that fits into the slot. In the ankle, the lower ends of the tibia and fibula form a bracket, the mortise, and the dome of the talus fits up into this bracket as the tenon. This bony embrace gives the ankle remarkable stability, particularly against side-to-side forces. The broad dome of the talus is wider at its front than at its back, which means that when the foot is dorsiflexed, toes pulled up, the widest part of the talus is wedged tightly into the mortise, creating a very stable, locked position. When the foot is plantar flexed, toes pointed down, the narrower part of the talus is in the mortise, allowing more play, which is why ankle sprains most commonly occur in plantar flexion. The fibula, which forms the lateral wall of the mortise, does not bear much of the body's weight directly. That passes mainly through the tibia and talus. But it contributes significantly to ankle stability through its joint with the talus and through the strong ligaments connecting it to the tibia. The ankle's mortise design reflects a fundamental engineering principle: stability achieved through shape, with the geometry of the joint itself constraining unwanted movement. Forensic anthropologists and geneticists have developed increasingly powerful methods for identifying individuals from even small fragments of skeletal material. Traditionally, this relied on morphological analysis, the shape, size, and distinctive features of bones, combined with circumstances of discovery and any associated evidence. Today, DNA analysis from bone has transformed the field. Modern techniques of ancient DNA extraction and sequencing can recover genetic information from bones thousands of years old, allowing definitive identification of individuals where DNA from potential family members is available for comparison. The petrous portion of the temporal bone, as noted earlier, is particularly valuable because of its exceptional density and the resulting preservation of DNA within it. Isotope analysis offers another powerful tool. The mineral composition of bone reflects the chemistry of the food and water consumed during life, which in turn reflects the geological environment of where a person lived. By measuring the ratios of isotopes of elements like strontium, oxygen, nitrogen, and carbon in bone and tooth enamel, scientists can sometimes reconstruct an individual's geographic origins and movements during life. These combined approaches, morphology, DNA, isotope chemistry, have been used to identify the remains of historical figures, to repatriate the remains of indigenous ancestors, and to identify victims of mass disasters. Each bone fragment, however small, carries within it a wealth of information about the life it once supported. The arm connects to the skeleton only through the sternoclavicular joint. The glenohumeral joint links the arm to the scapula, which itself connects to the clavicle at the acromioclavicular joint. The clavicle then meets the sternum at the sternoclavicular joint, the sole bony connection between the arm and the axial skeleton. All forces between the arm and trunk, pushing, pulling, lifting, and throwing, pass through this single joint. Its articular surfaces are small and bony. Congruence is limited, so stability depends on a strong capsule, ligaments, and a fibrocartilaginous disc. Spontaneous dislocations are rare, but when they occur, often due to high-energy trauma, the consequences can be serious because of nearby vital structures. Despite its modest size, the sternoclavicular joint is remarkably adapted. It allows subtle gliding and rotational movements that accommodate the scapula and arm while maintaining a secure link to the central skeleton. Its combination of mobility and resilience demonstrates how a single small joint can manage the mechanical demands of the human arm. The osteocytes, the most abundant cells in mature bone, are embedded in mineralized matrix and cannot move. To communicate and receive nutrients, they extend long processes through tiny channels called canaliculi, linking with neighboring osteocytes and cells lining nearby vascular canals. This network allows exchange of nutrients, waste, and signaling molecules, resembling a neural network spanning the entire bone. Osteocytes sense mechanical strain. When bone is loaded, fluid flow through canaliculi changes, stimulating them to signal remodeling, adding bone where needed, removing it where not. A single cubic centimeter of cortical bone contains thousands of osteocytes, each connected to many neighbors, forming a dense, interconnected web. This intricate network quietly translates mechanical forces into biological responses, maintaining the skeleton's strength and integrity through a hidden chemical conversation within the bone. We noted earlier that the skull vault contains fontanelles, soft areas between the developing bone plates in the infant skull. The largest, the anterior fontanelle, can be felt as a soft, pulsating spot, with the pulse transmitted from underlying blood vessels through the thin covering. The anterior fontanelle usually closes between 12 and 18 months. The smaller posterior fontanelle closes within 2 to 3 months, and additional smaller fontanelles at the sides close in the first few months. These gaps allow the skull to compress during birth, letting the head mold slightly to pass through the birth canal and return to normal shape afterward. Fontanelles also provide clinical insights. A bulging fontanelle may signal raised intracranial pressure, while a sunken one may indicate dehydration. Gently palpating an infant's head thus offers important information about their health and development. Adolescence brings one of the most dramatic periods of skeletal change since infancy. Rising sex hormones, estrogen and testosterone, and growth hormone accelerate activity in the growth plates, lengthening bones rapidly. The growth spurt can add 5 to 10 centimeters of height per year at its peak. The timing differs between sexes. Girls usually begin between 10 and 13, briefly surpassing male peers, while boys' later spurt ultimately results in greater final height. Bone proportions shift as well, with leg bones growing faster than the trunk, producing the leggy appearance. Hands and feet also grow rapidly, sometimes appearing large before the rest of the skeleton catches up. The pelvis widens in girls under estrogen, forming the mature female shape, while males see broader shoulders partly through clavicle growth. These changes are recorded in the skeleton. Growth plates, proportions, and ossification mark the dramatic transformation of adolescence. It is easy to think of the rib cage as a static, protective structure. But the ribs are never still for more than a moment. With each breath, they rise and flare during inhalation, descend during exhalation, and the thoracic vertebrae, costovertebral and costotransverse joints, and costochondral junctions all flex slightly. The diaphragm, a dome-shaped muscle forming the thoracic floor, contracts and flattens during inhalation, increasing thoracic volume and drawing air in. Relaxing during exhalation, it rises and gently expels air. External intercostals lift the ribs upward and outward, while internal intercostals assist forced exhalation. This continuous, involuntary motion occurs 15 to 20 times per minute for a lifetime, totaling roughly 600 to 700 million cycles over 80 years. Right now, as you rest, your ribs move quietly, slowly, with each breath. The skeleton itself is breathing. Along the lateral side of each thigh runs a thick band of dense fibrous tissue called the iliotibial band, or IT band. Originating from the iliac crest and attaching to the lateral tibia below the knee, it contains no contractile tissue, but is a reinforced portion of the fascia lata surrounding the thigh. Tension in the IT band is maintained by the tensor fasciae latae at the hip and the gluteus maximus, aiding lateral stability of the knee during walking and running. Friction between the band and the lateral femoral condyle can cause iliotibial band syndrome, producing outer knee pain that worsens with activity. More developed in humans than other primates, the IT band reflects adaptation to bipedal locomotion, stabilizing the stance leg during single leg support. It is a structural element of the skeleton's soft tissue frame, shaped over millions of years for upright walking. The face we present to the world is largely shaped by the underlying bones of the facial skeleton. Cheekbone prominence, eye socket depth, nasal bridge breadth, chin projection, and forehead height are all determined by the size and shape of these bones. The zygomatic bones form the cheek's bony prominence and the outer orbit margin, while the maxillae support the upper face and teeth. The frontal bone shapes the forehead, and the mandible defines the jaw and chin. Overlying soft tissues modify contours, but the bone provides the fundamental structure. Plastic surgeons know that altering facial appearance after trauma or congenital anomaly requires changing the bone, as soft tissue alone cannot correct skeletal deficiencies. Subtle differences in bone angles and projection across individuals create the extraordinary variety of human faces, rooted in the same basic skeletal framework. Each of the 12 thoracic vertebrae is defined by its articulation with a pair of ribs. The rib head meets facets on the vertebral body, and the rib tubercle meets a facet on the transverse process, forming the costovertebral and costotransverse joints. These allow the small rotation needed for breathing while maintaining stability. Because of these rib connections, thoracic vertebrae are less mobile than cervical or lumbar vertebrae. The ribs and sternum create a relatively rigid cage, limiting flexion, extension, and rotation. This region also forms the thoracic kyphosis, the gentle backward curve of the mid-back. Hyperkyphosis, common in older adults, results from vertebral compression fractures that wedge the spine forward. Despite limited mobility, the thoracic vertebrae are essential structural nodes, linking the ribs, arms, and spine while supporting both skeletal stability and respiratory motion. When we think of walking, we tend to focus on the legs, but walking is a whole body activity involving bones from the toes to the skull. Each step engages the pelvis rotating and tilting, the spine counter-rotating, the arms swinging to balance, the foot bones flexing and distributing weight, and the head remaining relatively still as the body moves beneath it. This coordinated pattern, the gait cycle, has been studied in detail. Biomechanists use motion capture, force plates, and electromyography to analyze how forces are generated, transmitted, and absorbed by each joint and bone. The pelvis's rotation increases stride length efficiently. Shoulder and arm counter-rotation reduces trunk torque. Foot arches and leg tendons store and return energy. And the head stability is maintained by the cervical spine and neck muscles. Walking is among the most energy-efficient forms of locomotion, and much of this efficiency comes from the skeleton's precise, coordinated movements, honed over millions of years of bipedal evolution. The base of the skull, the inferior surface supporting the brain and allowing nerves and blood vessels to pass, is one of the most structurally complex areas of the body. It is formed by multiple bones, the frontal bone at the front, the ethmoid and sphenoid in the middle, and the temporal and occipital at the back. This region contains numerous foramina and intricate chambers, the middle and posterior cranial fossae, internal acoustic canals, hypoglossal canals, and more. The sphenoid bone occupies the central portion, its body housing the pituitary gland in the bony sella turcica, or Turkish saddle. The skull base is critical in neurosurgery. Tumors here present major challenges due to nearby nerves and vessels. Endoscopic approaches through the nose now allow safer access with less disruption. In its complexity, the skull base exemplifies the skeleton's character, an intricate structure shaped by millions of years of evolution, where form and function are inseparably linked. After death, skeletal preservation begins, a gradual transformation of biological tissue into what may eventually become a fossil or archaeological specimen. The process depends heavily on the environment. In dry, arid conditions, bones can remain intact for thousands of years, though they become brittle. In waterlogged, acidic soils, bone may dissolve, while in other contexts, organic components degrade, leaving a fragile, mineral-rich residue. Mineral replacement can gradually convert bone into rock-like material, marking the start of fossilization. At a microscopic level, bacteria, fungi, and other organisms break down the bone matrix. These patterns, studied in histotophonomy, can reveal details about the burial environment and preservation conditions. The survival of any skeletal record is remarkable. Most individuals who have ever lived leave no trace. What remains is a tiny, biased sample shaped by geography, climate, and chemistry, from which we reconstruct the history of our species and skeleton. The olecranon process of the ulna, the prominent point of the elbow, forms the posterior end of the C-shaped trochlear notch, which wraps around the humeral trochlea like a wrench around a bolt. This provides the primary hinge of the elbow, allowing flexion and extension. The trochlear notch is highly congruent. The bony surfaces fit closely, and collateral ligaments supplement this congruence, making the elbow inherently stable. Everyday dislocations are rare and usually require unusual force. The coronoid process at the front of the trochlear notch stabilizes the elbow against backward directed forces. Fracture of this process during dislocation compromises stability and complicates treatment. The ulno-humeral joint's clean hinge mechanics have informed prosthetic elbow design. Engineers and surgeons study its precise motion to replicate natural kinematics in artificial replacements. Gout is a condition in which uric acid crystals deposit in joints, causing intense inflammatory attacks. Elevated blood uric acid, due to diet or genetic factors, leads to crystal formation. The joint at the base of the big toe is most commonly affected, though any joint can be involved. Urate crystals provoke a severe inflammatory response, producing sudden pain, swelling, and redness, often at night. Chronic hyperuricemia leads to deposits called tophi in soft tissues, and sometimes within bone, eroding adjacent bone and creating characteristic X-ray features, pitting and overhanging margins. Gout has a long history, known since antiquity, and dubbed the disease of kings due to its link with rich diets. Skeletal evidence of gout has been identified archaeologically. Henry VIII is widely believed to have suffered from it, with analyses of his remains showing consistent bony changes. Pregnancy places unique demands on the female skeleton. As the uterus enlarges and the center of gravity shifts forward, the lumbar spine increases its lordotic curve to maintain balance, contributing to low back pain in many women. The pelvis adapts for childbirth under the hormone relaxin, which increases ligament laxity, allowing pelvic joints to widen slightly. The pubic symphysis can separate by a few millimeters, facilitating passage of the baby. Some women experience discomfort in the pelvic joints, known as symphysis pubis dysfunction or pelvic girdle pain. Calcium requirements rise during pregnancy and breastfeeding, as the developing baby and milk production draw on maternal stores. If intake is insufficient, bone may be temporarily demineralized, though density typically recovers afterward. These skeletal adaptations show that bone is not a fixed structure, but a dynamic participant in the body's profound physiological events. When anatomists began naming the bones systematically, they drew on Latin and Greek, choosing terms that described shape, location, or distinctive features. This tradition created a vocabulary that, though complex, carries quiet poetry. The humerus means shoulder or upper arm. The patella means little pan. The fibula means pin, referencing its slender shape beside the tibia. The tibia means flute, perhaps due to its shaft. The calvaria, the top of the skull, relates to bare or bald. The sacrum's sacred etymology has been noted. Vertebral processes also bear descriptive names. Spinous processes project posteriorly like a spine. Transverse processes extend outward like bars, and articular processes bear smooth facets for joint articulation. Knowing these names is to carry a small library of classical description, a language capturing the skeleton in terms of form, location, and function, preserved from the scholars who first sought to describe it. The skeleton each of us carries is not an invention of humans. Its fundamental plan, skull, vertebral column, paired limbs, rib cage, is shared across vertebrates and originates in fish-like ancestors from over 400 million years ago. The earliest bony vertebrates appeared in Silurian and Devonian seas, leaving mineralized fossils in ancient rocks. The transition to land, the evolution of tetrapods, involved dramatic skeletal changes. Fins became limbs, vertebrae adapted to support weight, and the skull restructured for new sensory and feeding demands. Yet the basic elements, spine, skull, paired appendages, persisted. Over hundreds of millions of years, the bony skeleton has proved versatile, forming wings, flippers, claws, hooves, horns, crests, and tusks. Its essential character, a mineralized framework of living tissue, growing and remodeling throughout life, has remained recognizable across vertebrates. When you think of your skeleton tonight, consider that it carries within its very structure the record of 400 million years of refinement. Ancient, patient, and wise. We have arrived, at last, at our final fact, and it is perhaps the most personal of all. The skeleton you carry inside you is not just support. It is a record of everything you have been and done. It shows your ancestry, diet, activities, injuries, and the physical demands placed on your bones. Its mineral composition and joint surfaces reflect your life, while its proportions carry the inheritance of generations. Long after other records vanish, your skeleton endures, a durable biography written in mineral and collagen. The bones beneath your skin have carried you through every moment, supported every step, and silently maintained your body. They are extraordinary, and they are entirely, specifically, uniquely yours. We have wandered tonight through 100 quiet rooms in the human skeleton. We began with the simplest facts: the number of bones, their living tissue, their earliest formation, and explored joints, minerals, fossils, and the stories preserved in bone. We saw the tiniest bones of the inner ear, the densest petrous temporal preserving ancient DNA, and the femur shaped by stress with every step. We heard the ribs breathing, the spine lengthening, and the marrow building blood. From embryonic bone cells to fossilized ancestors, bones record diet, health, place, and occupation. They communicate with the brain, respond to mechanical forces, and continually remodel themselves. Even now, osteoblasts deposit mineral, osteoclasts dissolve old tissue, discs rehydrate, and marrow produces blood. The skeleton is never still, never silent, quietly supporting life as you rest. In the long history of life, the skeleton has been present for hundreds of millions of years, shaped by evolution into the structure that supports you now. Ancient wisdom in mineral and protein, handed down through generations. The bones that carry you tonight have been developing since before you were born. They have endured every fall, every illness, every demand of your life, working without instruction, quietly taking care of you. As you settle into the night, know the skeleton knows what to do. The bones will be there in the morning, as patient and solid as they are now. They have supported you through every moment, asking only that you rest. Remember the tiny stapes carrying sound, the femur's honeycomb interior, the smooth skull vault cradling the brain. Breathe slowly, feel your ribcage expand and fall. Your spine lengthens, discs rehydrating, bones at rest with your body. If you have made it here, through all 100 facts, through the quiet corridors of the human skeleton, then you have done something lovely tonight. You have learned a little, wondered a little, and spent time with one of nature's most remarkable structures. The skeleton has been with you your whole life. It will be with you tonight, and in the morning it will rise with you, quiet, patient, steady, ready to carry you into another day. Let your eyes stay closed. Relax your jaw and tongue. Feel the weight of your arms, the gentle press of your body. There is nothing to hold on to tonight. Your breath slows. Tiny cells are building and rebuilding, the ancient rhythm of bone continuing as it always has. The bones are content. They are doing what they do. You can rest now. The bones are resting. The marrow hums softly. The tiny ossicles of the ear are still. Sleep well. Good night.